Joining us. I'm Tom Pollard. I'm Dean of the Graduate School, and I'm glad to open our Company of Scholars series for 2014 with a talk from my friend David Evans. I knew David Evans before he had no, it's just on for him. I got to go to the podium. Okay, I guess that's okay. Is that better? Hear better now? Okay, great. I'm Tom Pollard. I'm Dean of the Graduate School. I'm a biologist. And welcome to our series for 2014, the Company of Scholars Lectures, which is a series of lectures that the Graduate School sponsors to provide to the community some lectures of general interest on many different topics. David Evans, our speaker today, was known to me as a fabulous university citizen because I knew him from promotions committees and other virtuous activities that he was engaged in. And then suddenly, a couple of years ago, he had this very high-profile paper in Nature that got in the newspaper and so on. And I was suddenly aware of the very, very interesting work he was doing, which he's going to talk about today. Because I think we all know that the continents have been drifting around on the surface of the Earth, but what he and his friends managed to do is figure out where they're headed, which is pretty interesting, and because it's going to have a big impact on all forms of life on Earth, as you'll hear in the lecture. So this is the first of three lectures we're having. The second one is by Susan Hyde from the Political Science Department, which is on March 25th. She does research on elections, and her topic's going to be, does democracy promote democracy? Interesting question. And then Gary Tomlinson, who's sitting right back here, is going to speak on the 16th of April about 1 million years of music, which sounds like another fascinating topic. Looking back in time like our speaker today, and perhaps forward, I don't know. Okay, David is the Yale College graduate and got his PhD at Caltech and did a postdoc in Australia where he was working on some of the same things he's talking about today, I believe. He joined our faculty here in the Department of Geology and Geophysics in 2002 and was promoted to associate professor in 2007 and full professor in 2009. And you can see his title before you. David, welcome.
Thank you very much for coming today. I will be stepping away from the podium, so I hope you can hear me in the back. Good, excellent. And I imagine that a catchy title such as this may have drawn more of a broad crowd in Yale, and I hope that's the case, and I hope to intrigue you not only for the portion of my research which will occupy the middle of the talk, the first two-thirds of the talk, but also some speculations here at the end on what a geologist, not all geologists, but a geologist's perspective, mine, on the ultimate fate of humankind. So we're going to begin actually with some audience participation, and I'm very curious what your views are in terms of where humanity will be 50,000 years from now. And so if you have an internet mobile device, you can go to this website, polev.com/majestic, or you can text 22333 and submit your answer to this multiple choice question. There is no right answer. This is far in the future. But where do you think humans will be 50,000 years from now? We have various options. We have natural extinction at the top. The first four are extinctions, the last two are survival. The votes are coming in. Natural extinction, which might be a meteor impact or a supernova blast or a pandemic disease. We have man-made extinction, maybe nuclear holocaust. We have extinction or transmutation by religious apocalypse, think the second coming, if you will. Conquest or annihilation by extraterrestrial civilizations. And then the last two are what I imagine very, very broadly what a possible, maybe optimistic scenario might be. Would we have a sustainable existence that's confined to Earth and perhaps just the inner solar system, the rocky planets, the Moon and Mars, but maybe just Earth? Or the Star Trek solution, which is expansion into deep space. So I'll give you a minute or two to register some more votes. If you are joining us from the cyberspace, the cyber universe on the streaming. Your votes should also count here. So as I watch some more votes come in, we have more of a pessimistic crowd perhaps in the audience today, a few more optimists coming in. But what's interesting is that when I tried this on my students in geology class I'm teaching now, I got a lot of questions about what about global warming, and do you consider that to be natural or man-made? Actually, I left that up to the audience. I think you will find, maybe I'll come back to that issue. Personally, I don't think global warming is capable of causing the human extinction. It might make us very uncomfortable. Okay, so this poll will continue to go on, and we have more optimists, and we have somewhere between a confinement to sustainable existence on Earth and the Star Trek solution registering there. So I'll return to this at the end and register some of my opinions as they come in. So we'll put this in the background and click it out, and here we go. So the talk will be in 3 parts. First, I'm going to introduce to many of you, I'm assuming no prior advanced knowledge in geology. I'll give an introduction to geology and what we call deep time, millions of years or billions of years in the past. And then that will segue into my research, which is the past and the future motions of continents across the Earth's surface using the magnetism of rocks. And then finally, we'll return to the subject of perhaps the ultimate fate of humankind. So to begin with, I will start with the concept of deep time and walk you through some of the most important events in the history of Earth and life on Earth from our perspective. And so the concept of deep time is one where you have to imagine a time scale. And the time scale can be shown vertically or horizontally. You'll see both in this talk. But vertically, it extends from the bottom. In geology, we think of layers of sediment recording events in Earth's history. So from the very bottom, 4,600 million years ago, the creation of the solar system, moving all the way up geological time and the evolution of land plants and reptiles and birds and dinosaurs, to finally humans up to the very top. And this kind of figure is what you might find in any introductory geology textbook or many popular websites. But notice that the time scale that's employed is nonlinear. And what that means is that most of Earth history, 88% of Earth history, in fact, is shoved down here at the bottom because, frankly, we don't know a whole lot about it relative to how much more information we have from the relatively recent geological past. And if we were to plot things appropriately in a linear time scale, that 88% of geological time, which is known as the Precambrian, that means prior to the Cambrian radiation of animal life on Earth, this huge window of time is really my playground for research because there's recent technological innovations which have opened up the possibility of doing the research that I do in Precambrian time. And what I hope to show you is that a lot of our natural resources, and particularly our metal resources, come from Precambrian rocks. And so part of the industrial society and the excellent lifestyle that we enjoy right now is based on a long history of processes that occurred in this time, which until relatively recently was somewhat mysterious to us. So let's start from the very beginning, and a little eye candy for you, a simulation of the moon-forming impact shortly after the initial accretion of the Earth and a companion body thought to be about the size of Mars that collided and ended up ejecting a whole lot of material from both bodies, much of which got fragmented and much of it was reaccreted to a very glowing hot Earth protoplanet, some of it accreting in waves. And what you don't see in this image is the moon coming out at about 20 Earth radii away and forming from that initial event. So there's various ideas in current research about how this may actually have happened, but the giant impact theory is really the birth date of effectively the Earth as we know it. Fast forward 1 billion years, 1,000 million years from that event, and we find the oldest tangible evidence of life on Earth. And it's a very humble evidence at that. These are called stromatolites. and they are found in places such as Western Australia and South Africa, two of the oldest well-preserved areas on our planet from this age. 3.4 G, A, and G stands for giga, A stands for annum, so a billion years ago, 3.4 billion years ago. We have the suggestion that biology contributed to making these conical layers, these conical structures in the rocks. And then there is some debate, of course, about whether these are truly biological. If there is any scientific consensus, it is based on the comparison broadly between these forms and similar forms today, either in the Bahamas underwater, or as you can see, if you drive a full day's drive north of Perth, Western Australia, where I did my postdoc, you can go to Shark Bay and you can see these noble and humble creatures building these cyanobacterial mounds in the shallow sea. So this is the suggestion of the oldest life on Earth at about a billion years after the formation. From there, we can continue on with the Tree of Life. And the Tree of Life, as many of you know if you're a biologist, has three great superkingdoms. Those of the eukaryotes, which include animals, plants, and fungi, as well as protists. Those of the bacteria, and those of archaea, which were thought to be bacteria for a long time until it was realized that archaea are as different from bacteria as we are. But they are single-celled. And various estimates based on geological chemical markers that are preserved in sedimentary rocks suggest the various ages for nodes of branching along the Tree of Life. We finally get up to animals here, and there we are of course, we place ourselves at the top of this tree next to our closest evolutionary relatives, which are mushrooms and corn. So this, I hope, gives you some perspective on the diversity of life on Earth and how small we multicellular creatures are in that kind of context. Another very, very important event, fast forwarding again another billion years. In this case, now we're looking at a timeline which goes from 4.5 billion years ago to the present, and we're looking at a plot of estimates of oxygen in the atmosphere. And today we have about 20% oxygen in the atmosphere. It's what we breathe to survive. But there was about the first half of Earth history when oxygen levels were vanishingly low. And this is a logarithmic scale, so each tick is a tenth less, a 10% of the tick above it, of the oxygen concentration. So here we are at present with about 20% atmospheric oxygen, but you go back about a half a billion to a billion years, and you might be looking at 1% of that fraction. And before that, even less. And obviously, advanced life as we know it, ourselves, could not exist without the evolutionary innovation of oxygenic photosynthesis within the life domain, to produce O2 as a waste product, and then the rest of life had to respond to this abrupt rise. So this is one of the major events in life history. Now, we go forward another 1.5 billion years, and we get to a concept which is called Snowball Earth. And Snowball Earth is the concept and the hypothesis which is gaining support through the years, I think, which is that the Earth, on at least 2 occasions, and perhaps as many as 5 occasions, around 600 to 800 million years ago, completely froze over, and froze over for as long as a few million years at a time. Life would have needed to exist, we know, because we have the antiquity of the fossils with extant microbial organisms. Life would have had to exist under the ice, but it was very, very extreme challenges. And in fact, some of the research that I do on the magnetism of rocks gives us indications that some of the ice deposits in these times were close to the equator of the Earth, and by inference, the entire Earth should have been covered. But that would be a separate talk in itself, or perhaps even a semester course on the Snowball Earth hypothesis. What I'm hoping to do just now is give you these insights, these little snapshots and important evolutionary events in Earth history from a biological perspective, from the moon-forming impact to the oldest tangible evidence of life in the stromatolites, to the rise of oxygen, to these globally engulfing ice ages. These all set the stage for the Cambrian radiation of animals that happened abruptly about 540 million years ago. Now, if we were to truly appreciate this amount of time, the 4 billion years of Earth history prior to the Cambrian radiation of animals, I find it instructive to make an analogy with a calendar year. So if we begin a calendar year on January 1st, we get to June before we have the oxygenation of the atmosphere. We get to mid-November before we have the Cambrian radiation of animals. And you can see these various other events which occurred in a more recent geological time, all basically happening in December. The large coal swamps on the 1st of December. The largest extinction, the Permian-Triassic boundary, 250 million years ago. By this calendar analogy is on December 11th. The dinosaur extinction on Boxing Day, the day after Christmas. And then finally humans come along at, if you include our Australopithecine ancestors as nominally human, they show up at about 8:10 p.m. on New Year's Eve. In fact, all of civilization, let's be generous and give ourselves 8,000 years of agrarian society. The technology that we use to become an agrarian society, do things like control yeast to ferment alcoholic beverages, that technology was invented 55 seconds before midnight. Perhaps just in time, you might say. Okay, so with that introduction to broad expanses of geological time, I'm going to shift gears and tell you a little bit about the dynamic motions of the Earth's surface and interior. And to appreciate that we have plates on the Earth, we can find this animation of earthquakes happening within a 3.5 decade interval from the latter half of the last century. And this is just passive recording and location from a series of seismic networks around the world of where the earthquakes are happening. And as time moves on, it becomes clear that the Earth's surface is divided into a series of internally mostly rigid plates where there are no earthquake epicenters, separated by relatively narrow zones of lots of earthquakes. And this is the surface expression of motions in the interior of the Earth, which are helping the planet release its heat to space. And again, it's a fascinating subject in itself. But for my purposes, I'm interested in tracking the long-term history of the motions of those continents as allowed by the presence of these plate boundaries that allow the relative motion of these large tectonic plates, which are internally rigid. So this is how a geologist would look at the map of the world and see the plate boundaries. Each plate is shown in a different color. Some plates are entirely oceanic in character. Some plates carry continents with them. And notice that the edge of the continent is not necessarily a plate boundary, as we have, for example, right here in Connecticut. So for this reason, we don't have major earthquakes where we are at the edge of this side of the continent, and yet California and Alaska have earthquakes at the edge of that side of the continent because that side of the continent coincides with a tectonic plate boundary. So with that introduction to the Earth system, both in time and space, I can now tell you a little bit about my research. I'm sure many of you have heard about the supercontinent known as Pangaea, which started to break apart about 200 million years ago. At that time, the initial time of breakup, a position that's close to us here in Connecticut was within perhaps a long journey's walking distance from Morocco in the Western Sahara. And, when in the last 200 million years, we had a rift system that spread North America away from Africa, and in doing so, opened up the Atlantic Ocean and carried us farther and farther away, not only from our initial counterpart position in Morocco, but also far and far away from this tectonically active mid-ocean ridge, thereby allowing us to live in a tectonically quiescent environment today. So, but this kind of animation it's actually relatively easy to do, and it was first done in the 1960s, and it was made possible because of magnetic variations that were observed by ships towing magnetometers across the surface of the ocean. And we could, as soon as we understood the structure of the ocean, of the seafloor, of the ocean basin, we were able to, in a sense, replay the movie backwards and draw this new ocean lithosphere back down the ridge to go backwards in time. So the solution of the Pangaea puzzle is a relatively simple one by tectonic terms. And to give you a sense of the kind of geological structures that rifting has left behind in Connecticut for your local amusement. We can look at the geological map of Connecticut, which was most recently compiled by a very famous Yale geology professor named John Rogers. And what you see in here are every color represents a different rock type across the state. And so you can go from one place to another and you can draw a map and you know where you are and you find a rock type that's distinctive, and you plot your position on the map and you can trace these rock types around. And the red in this case corresponds with igneous rocks. These are typically volcanic rocks, and they are associated with that tearing apart of the crust 200 million years ago. Such rocks include West Rock and East Rock and Sleeping Giant and the Hanging Hills of Meriden. These are direct products of that tearing apart of the crust 200 million years ago. They are embedded within a series of sedimentary rocks that were formed in a great rift valley. So if you imagine what Connecticut was like 200 million years ago, you can think about going to East Africa today and seeing a big rift valley pulling apart. On either side of the central rift valley, we have what we call the western highlands of Connecticut and the eastern highlands of Connecticut. Highlands in a relative sense, of course. And in these areas, the geology has patterns that swirls around as if it was taken in a butter churn and swirled around, or in a mixing pot of doughy bread. And that's exactly what happened 100 million years prior to the rifting, because Connecticut was the site of a great collision zone. Looking at the geological map of Connecticut in a much larger context, of course, geology knows no political boundaries, so we can extend the central rift basin into central Massachusetts, and it dies out right around the Vermont-New Hampshire border. There's an equivalent basin throughout most of New Jersey, one in Gettysburg, and a series of these cracks in the earth that failed to develop into an oceanic rift. However, you can see, aside from those rift valleys, all these bright colors of greens and purples and pinks and oranges. These show what's called a tectonic fabric, an organization of the rocks, which you can almost imagine looks like someone took a carpet and rucked it up, and we're looking at the great corrugations of folds across the Appalachians. And that's what we think actually happened about 300 million years ago, when what was before in West Africa collided with what was in North America. So we had the continents colliding at 300 million years ago and tearing apart at 200 million years ago. So the supercontinent Pangaea existed for that 100 million years. And during that time, we would have expected the site of Connecticut to be truly a great mountain range, something like the Himalayas. If we imagine an artist's conception of a cross-section of the mountain range that created the Appalachians, you see all those swirly patterns that you saw expressed in the geological map of Connecticut and New England. And you can almost imagine the movie that must have occurred to produce the compression on this cross-section and the landscape that may have existed at that time. So if we now go globally outward and think about what Pangaea looks like from the perspective of its constituent elements, we can identify within a Pangaea base map the ancient continent of North America plus Greenland, which is colored in yellow, and the ancient portion of Africa, which is colored in brown. It's called the West African block or craton, and various other pieces of either South America or Central and Southern Africa or India, Antarctica, Australia, as well as Northern Europe and Siberia. And the Pangaea continent is composed, according to lots of geological studies that have mapped the areas and recognized compatibilities of geology from one region to the other, it is composed of a series of building blocks which did all collide and come together. And that is represented on this map by these black regions with the red outline. Those are the collision belts, the great mountain ranges that welded Pangaea. If we were to remove those, we can now see the building blocks that we would like to put together in an arrangement that existed prior to Pangaea, and that is the principal puzzle that I'm trying to solve in my research. Where was West Africa relative not only to North America, but relative to Amazonia, relative to the Congo block or Congo craton, relative to the Southern African block or called the Kalahari craton? There are about 13 pieces in this puzzle, and since I've been doing puzzles since before I could speak, basically, I find this to be an extremely frustrating puzzle because with only 13 pieces, how is it that we cannot solve this so easily? Part of the problem is that the picture on the puzzle has been partly erased by subsequent geological events, and of course there is no box by which we can see the answer to that puzzle, as well as a lot of these collisions have tended to wear down the jigsaw locking edges. So it's not as simple as a jigsaw puzzle, but we are making some progress one piece at a time. And the way we are making that progress is by looking at the magnetization of rocks and realizing and appreciating the fact that Earth's magnetic field, which is generated in the outer core of the Earth from the liquid motions in the outer core, sends off field lines that go through the Earth's surface and out to space and back through the Earth's surface and back into the interior of the planet. Those field lines have a very consistent relationship with the geographic latitude of an observer anywhere on the surface of the Earth. And that relationship is such that qualitatively, if you're at the North Pole, the magnetic field lines are straight down. If you're at the South Pole, if you're standing at the South Pole and looking upside down in this figure, it looks like the field lines are coming straight out of the ground, going upward. And if you're on the equator, the field lines are tangential to the Earth, or they look like they're pointing straight flat to the north. And the angle of intersection, that vertical angle of intersection between the Earth's surface and these field lines, very systematically, according to this formula, where I is that vertical angle, we call it the inclination, and lambda stands for the latitude on the surface of the Earth. And a couple of trigonometric functions, and that allows us to take a rock sample that formed many millions of years ago, understand that the geological context in which that sample was taken, such that, for example, if it's in a series of sedimentary layers or volcanic layers, we know that those formed horizontally, and therefore they formed a nice approximation of the Earth's surface, measure the magnetic direction in those samples, and therefore obtain this inclination, and from that we can infer the latitudes. So this information is what we will use to draw maps of the ancient world, one block at a time, and many, many ages at one time. So we need to go into the field and collect a lot of rocks from a lot of different ages. I'm usually asked by lay audiences, how do you know where to go? And the answer is all of those geological maps that had each color for the different rock types. Those are done not only at the scale of the state of Connecticut, but also quadrangle scales. They can be very detailed maps. With the information that's obtained independently for dating the rocks, we can target where precisely we want to go, whether it's here in the Australian outback or anywhere else in the world, to collect our samples. When we do collect our samples, we can do it by using a hammer, but the more fun and interesting way is to have a portable rock drill, which is essentially a chainsaw, which we've modified to have a diamond bit drill bit on the end. And we drill out a little core sample, and before we break that core sample out from the rock, we can put in a specialized orientation device in the rock when the sample is still inside, and we can measure both the horizontal azimuth of that core and the vertical angle of that core. So we can orient this rock sample that we collected, whether in Australia or anywhere else, and then when we take it back and put it in my laboratory, we can use the computer to rotate those directions into their field coordinates. The data look like this, and I won't belabor that point other than to suggest that this is in fact actually quite a complicated process requiring some art to being able to understand the data that we obtain, especially in very old rocks. My laboratory, where the measurements are done, looks like this, and we have an automated system where each of these little gray cylinders is a slice of one of those cores that we drilled in the field. Each one of these is placed on the tray with an orientation mark which is lined up with the 3D axes of our instrument, and the sample is picked up by a vacuum motor and held in place by suction while the chain rotates to a hole, drops it down, and just off the picture here is a very, very sensitive magnetometer that can analyze the magnetic strength not only in what you might think of strongly magnetized materials, but also just everyday rocks. It was once said when these were first invented in the 1970s, this level of magnetometer, that you could measure the magnetic direction in an apple core. And then, of course, in Australia, they actually did that experiment and measured the magnetic moment of an apple core. So we can take rocks or any materials that are not particularly magnetic, run-of-the-mill rocks that have interesting and well-known geological histories, and measure their magnetic directions, obtain that vertical angle, and get the latitude. So then when we try to convert that into plotting the data onto a map, I'm going to take you through a few minutes of this process. We can imagine looking down at the present North Pole, and I've taken away the other continents for simplicity, but here is a stylized map of the North American continent with the Great Lakes here, Hudson's Bay. And if a rock formed somewhere in the middle of North America, let's say close to Thunder Bay, Ontario, and it was magnetized as it formed today, then the magnetic direction here would be pointed like a compass needle toward the present North Pole, and that relationship between the vertical angle and the horizontal Earth surface would tell us the distance between the pole and the site. However, if we look at another rock, which perhaps may be from, say, the state of Wisconsin, which is, say, 450 million years old, and we take its magnetic directions and we measure those, we can see not directions corresponding to today's field, but we see them deflected in a different direction. And this is in fact a representation of the actual data from 450 million year rocks in Wisconsin. And we can, through mathematical and geometrical manipulation, compute an ancient position of the pole relative to the site. And that ancient position of the pole is different from the present North Pole. And then the last step we need to do is, if we are identifying the relative motion or relative position and location of a site and a pole, and if we want to reconstruct the continent now to its ancient latitude, you just do a rigid body rotation. You can imagine holding my arms as a rigid beam here, and we're going to shift the continent and this magnetic pole, shift it over until the ancient magnetic pole reaches the present North Pole. And that same shift that I applied to the continent gives rise to a reconstructed position of the continent, which at that time lay along the paleoequator. And I've added...
The pole doesn't move.
Yes, assuming always that the geomagnetic dipole axis is parallel to the rotation axis. And that is a fascinating subject of discussion. All of the tests that we have given that assumption have passed to within about 5% accuracy. When we average over a few thousand years and of time, and if we are willing to allow the freedom of not knowing a priori whether the magnetic pole that we're pointing to is a North Pole or a South Pole due to the fact that the magnetic field reverses occasionally. Thank you for that point of clarification. So we can say from these directions that the ancestral continent of North America lay along the paleoequator. We call it Laurentia. We know it was joined with another continent of Northern Europe called Baltica. And that is essentially how we go about doing these reconstructions. Now, I'm going to take you back to the initial assembly of fragments of North America back about 2 billion years ago, almost half of the age of the Earth, and show you some of the recent results from my laboratory that have given rise to a hypothesis, a model, that suggests that the current amalgam of North America, and for geographic reference, that is Lake Superior. This is the state of Minnesota, the 49 parallel border with US and Canada, and then much of the Canadian Shield is beautifully exposed ancient rock through Hudson's Bay and over toward Yellowknife, Northwest Territories. And what you see on this map are a series of pieces, if you want to call them puzzle pieces, you can, separated by these red and green zones, which are thought to be the sites of vanished oceans that closed along with the collision of all these blocks during the interval 1.9 to 1.8 billion years ago. Previous to our work, it was recognized that these suture zones, these tectonic suture zones, were the sites of vanished oceans that closed. But the prior configuration which even went as far as to name the oceans, Maniquan Ocean, Snowbird Rift or Ocean, didn't really know how wide those oceans were. So what my colleagues and I did a synthesis in the last couple of years where we are presenting a hypothesis that is dealing with magnetic data. And what we're looking at now is an animation of 400 million years of the assembly of North American continent. The ages in millions of years are shown up there, and so they're going by at a fairly rapid clip. The fragments of North America are color-coded to match the magnetic data, which are appearing as circles. If we have done our job right, those magnetic data are plotting along the rotation axis. And you can see that the data are sparse, and we need to appeal to a lot of other information to estimate where these blocks were. I'm going to point out one data point there, which is not ours, but it's one from the literature, which is fascinating and needs to be revisited. If it's true, then we'll have to modify the model. But what you can see from this diagram is that we are accounting for all the blocks, including, for example, Wyoming, which started off near where Wisconsin is and moves over to join Western Canada. And then Western Canada and Greenland assemble first, and then finally the portion of Eastern Canada comes in on the side at the end. And from this history of 400 million years, we have at least a working model now for the creation of the North American continent. And this took a lot of organization, and there's special software to be able to do this. And I'm sure it's wrong in many ways, but I'm very excited that we now have at least a template for further investigations. We've taken this now globally, and the fragments of North America now from time interval of 2100 million years, moving forward in time, the fragments of North America are plotted in the northern hemisphere and upside down in your orientation for reasons we think that we have various reasons to suggest that it was in the northern hemisphere at the time. Those are shown in yellow, and the other blocks of the world are color-coded according to what continent they form in now. And we can just imagine the millions of years going by as the current continents assemble for the first time. So we think offshore of northern Canada were the fragments of what would eventually become Siberia. Portions of Australia, shown in blue, still yet to come together. Portions of South America in light green and Africa in red. India in purple, still and Asian blocks in purple, northern India, southern India, far away from each other. Once again, this kind of model is tied loosely by a series of data which are being plotted in the northern hemisphere there. There's a lot of room for improvement, but what I'm most excited about is for the first time our community is being able to assemble some templates by which we can really look and set up a global hypothesis for some of these motions. All right. This can go on for another 400 million years, but I think we should move along. One of the key aspects of this interval of time in what we think was the assembly of the Earth's first supercontinent about 1.8 to 1.6 billion years ago, which has been called Nuna. That supercontinent is, the assembly and the breakup of that supercontinent is known globally as occurring during a time of many, many mineral resources. And another part of the project that I'm very excited about is that we, in addition to our magnetic results and our simple polygons that we're moving around the surface of the Earth, we are also integrating our work with extensive databases of the ages of rocks and mineral deposits. And if you're a mineral expert, you'll recognize that nickel and copper and platinum group elements go together, that gold and copper sometimes go together, iron oxide, copper, gold, volcanogenic massive sulfide deposits, lode gold, unconformity uranium, Mississippi Valley type lead zinc, SEDEX, sedimentary copper. All of these now can potentially be mapped and charted and move around with our grid to be able to see where these deposits formed, not on today's present grid, but more importantly, on the paleo grids and what was the tectonic environment. And these black symbols here are representations of where we think the ancient plate boundaries were that were accommodating these continental motions. So I'm very excited about this as an exploration tool for mineral deposits moving forward in time, and we will see this theme recurring as we think about long-term sustainability of our civilization. In fact, I think many of you may have thought that if I'm talking about projecting continental motions far into the future, that would have our bearing on the future of humankind. Actually, I think the more important aspect of our bearing on humankind is the work we're doing in the ancient Earth to be able to locate many of these mineral resources. So finally, we will go to the future, and we will talk about this paper to which Tom referred in his introduction. And that is the question of whether there will be another supercontinent. And we certainly have enough time left over to assemble new continents. A part of the next supercontinent is already being created in the amalgam, which is Eastern Asia. India has collided with Asia already. Australia is moving north and shows no signs of stopping as it plows through New Guinea and ultimately the Philippines and ultimately Taiwan and Japan to collide with Eastern Siberia. But what's less understood is whether, as a thought experiment, whether we might expect the current westward motion of the Americas to continue all the way across the Pacific and join Asia from that direction, or whether we expect the Atlantic Ocean to stop spreading and to turn around and become another collision zone in an accordion type of fashion of supercontinent cycle. Or in our paper, we made the alternative suggestion that the Americas have moved as far west as they are going to move, and thereafter are only going to move north-south. Australia, we know, has moved as far east as it's going to move and has already begun moving north. And to explain the details of this would require another hour, so I won't go through that. But one point I want to make is that this captured media attention because of the speculation and the broad thinking in terms of what could the world look like 50 to 100 or to 150 million years ago. But in reality, the disclaimer is that is all idle speculation and is not, in fact, science. Yes, it's a prediction, but if you set up an experiment that you need to wait 150 million years to see if it's verified, it's technically not really a scientific hypothesis. It was useful, however, as a thought experiment because it was our way of relating to people what we did find, which was science, which was a relationship between three ancient supercontinents and the two transitions between those ancient supercontinents, where we did find motion that would be akin to the Atlantic stopping, opening, and akin to the Americas moving north-south and not going any further west and not turning around to the east. But again, to explain that in detail would require rather advanced topics, so I'll leave it there for now. But just for your amusement, we can see, according to our model, 150 million years into the future, Australia arriving and crunching up the rest of Eastern Asia, and our long-awaited partners in South America joining us here in Connecticut. And so this was the Amasia model that is not science. It literally took me about 3 minutes to arbitrarily put these maps together. But they are a good way of thinking about where we sit relative to a long succession of supercontinents that may be coming and going. And the work that we were doing on the ancient supercontinents, I think, is actually scientifically testable as a hypothesis. So this did make a media splash just about 2 years ago this week. Two of my graduate students were my co-authors. They were first and second author, and they were able to handle all the media frenzy. New York Times did a very good job and suggested now we're looking down at the South Pole with both the current grid of continents and the future motion of closure of the Arctic Ocean, the ancient location of the center of Pangaea off on the equator underneath Africa. And the three predictions that we set up were that either the next Pangaea would form back where the old one was, or it would go all the other side, or we would have this intermediate one in between. Now, if any of you have done anything that has captured media attention, you can take all of these posts and find your harshest critics on the internet. So we have one critic who suggested that some PhD student got a 5-year grant and a $100,000 salary per year for the study's findings. I think we're still striving to give our PhD students $100,000 a year. Far from it. So we have that criticism. We have another criticism from this gentleman who was just flabbergasted at the paucity of intelligence to think that such inelegance could arise from Yale University. But then I think he kind of gives himself a little discredit by suggesting that thermodynamics' second law insists that could not happen. So anyway, you really get a good reality check on the societal framework of your science when you actually do make a media splash. However, there are some more positive assessments, and I'm always going to be grateful for this lady who has rendered her actually rather quite positive opinion about the work. Okay, so we continue to make progress in these past and future motions, and now I want to return to the final aspect of the talk, which is thinking now about the billions of years of evolutionary history and tectonic history of the Earth, thinking about where humans fit in this all. So we will return to the time scale and remember that humans come on the scene in a very broad sense with our Australopithecine ancestors at 8:10 p.m. Actually, on the same kind of calendar year analogy timescale, the countdown, the New Year's Eve countdown, would actually go 150 years per second. So if you would allow me, it would go something like Gutenberg, Renaissance, Enlightenment, Industrial, Happy New Year, right? So 150 years a second. And so I gave you a poll at the beginning of the lecture of 50,000 years into the future, because 50,000 years ago is, according to some anthropologists, about the time when we started to really emerge from our more primal roots, developing some music by that time, starting to work our way towards, certainly control of fire, work our way towards domestication, a little early before that. But so 50,000 years into the future is enough time to really think about, well, this could be a really long-term prospect for thinking about the human race. And I'll now register some of my own opinions about these 6 possibilities. The first one, the natural extinction by meteor impact or supernova explosion, I think the chances, geologically speaking, the chances of that are very small on a 50,000-year timescale. In terms of man-made extinction, this is, of course, a real possibility, but I would like to pursue a more optimistic agenda than that when I think about my own life's goals and so forth. Religious apocalypse and ET civilizations, I personally don't subscribe to. And then these 2 options for whether humans are going to survive either confined to the solar system or confined into expanding into deep space, a la Star Trek. Actually, the nearest star is about 4 or so light years away. There are planets orbiting around stars that are within, say, 10 light years from us. But the speed of light is so fast that for us to actually propel a vehicle to get there would take really, really long time. And I don't think 50,000 years is enough time to do it. So really, when we think about 50,000 years, my hope is that we will try to find solutions that really exist on Earth. Okay, we can talk about terraforming Mars and so forth, but that's very expensive. And I think we really should have our agenda on sustaining ourselves on the Earth. And if we think now in terms of human history from on the order of tens of thousands of years ago to the present, and an estimate that I found somewhere on the web in terms of, which I tried to fact check a little bit and it seems reasonable, of human population going from 0 up to 7 billion, which we just surpassed. Basically, it's a very, very slow, steady rise until the Industrial Revolution when things take off. Clearly, it's the unlocking of what some of my colleagues have called nature's treasure trove of the consequences of 4 billion years of tectonic mixing and concentrating some elements. not only in terms of mineral resources, but also, of course, our fossil fuels, that is allowing us to make technological advances and enjoy really unprecedented levels of prosperity globally that has allowed this population expansion to happen. And so we might think that prior to that technological development, the more or less sustainable population on Earth would be on the order of 100 million people. Okay? The question is, as we think about moving far into the future, looking at a very, very broad timeline, another timeline from left to right, several thousand years from now, people will look back at us and say, this was the oil age. And that oil age is a little blip. All right? Will the far side of that blip be reflected in a precipitous decline in human population back to the sustainable level? I don't know. Or will our engineers save us and harness renewable energies and recycle resources to be able to sustain us in the long term? You may have heard about peak oil. There's a lot of discussion about peak oil. This is one rendition that comes from an introductory textbook that I use. And this would be a more pessimistic view that we're already actually past the peak. Others will say that the peak won't come until another 100 years from now or 200 years. But regardless of when you think peak oil will be, when you stand back on a 10,000-year timeline, the age of oil is in fact a little spike. And I think there's no one who would argue with that, because oil just doesn't continue down at depth forever into the Earth. So let's talk about where those limited resources lie relative to what we might consider the economic growth of the planet. And if the economic growth is tied at all to the consumption of resources, we can consider several projections into the future. First, we can look at, and I am not an economist, and I know there's many degrees of freedom in very, very simple models that I created with Excel in the last few days. So this is not fancy by any means, but its simplicity is actually an advantage because I think I can understand the math that goes into this. So we'll start out with a level of 1 for today's both availability of resources and today's current consumption level. And let's suppose that annual economic growth, or economic growth in general, corresponds with a degree of consumption of resources. And it may not be a perfect fit, but it would be something along those lines. If you were an economist and you said, let's do 3% annual growth, that's a moderately healthy economy. It's not something that you certainly wouldn't be satisfied with it if you were a leader in the People's Republic of China, where you'd be looking for more like 5 or 10% annual growth. But it's a healthy economy. But by the timeline of 100 years from now, that kind of consumption vastly outstrips any model of the available resources. The ideally optimistic endowment is what I put as an upper limit, where we continue to find an equivalent of resources commensurate with what we've used already every 100 years. Okay? Every 100 years in the future, we find the equivalent of what we've already are using right now. And I call that ideally optimistic. You could maybe have it slightly more. We could have a more cyclical endowment of resources that awaits us through further exploration. And this is actually just a sine wave, and you'll see that later on. Or you can have a dwindling endowment of resources. And of course, some resources will follow more or less the optimistic level. Some will be more cyclical, and some will be dwindling. I heard a fascinating talk yesterday by Tom Gradle on the question of will metal resources become unaffordable to us in the near future. And I think his assessment was that the answer for some of those is yes. We can see that a 1% annual growth also outstrips the available resources according to any of these very simple models on the order of 200 years. But this 0.5% annual growth is getting able to respond to those. What if instead, though, we go to 1,000 years into the future? Well, now the 3% and the 1% and the 0.5% annual growth are all zooming up with that kind of curve that expands almost to infinity. The ideally optimistic endowment carries on, but it's not nearly enough to keep up with 0.5% annual growth. Cyclical endowment keeps going on very, very low, and dwindling endowment goes to 0. You could have a model which I think would be realistic for many resources somewhere in between, which would come up to some asymptotic value and then may be circular at some level in between this ideally optimistic model and another cyclical model. But let's now continue on the 50,000-year time scale, which I was asking you about with the poll at the beginning of the lecture. Now we have, with even our most ideally optimistic endowment, even that 0.1% annual growth has far outstripped the available resources within 5,000 years. And by even about 30,000 years in the future, even 0.02% annual growth vastly outstrips the available resources. So you can see with these kinds of curves that any kind of compounding annual growth will, at some point in time in the distant future, lead to a curve of that function relative to resources which are ultimately limited on the Earth. So this leads to the conjecture that truly long-term sustainability at any time scale into the future equals 0%, not 0.02%, not 0.01, strictly 0% economic growth. All right? And commensurate with that is that because resources are limited, we can't just throw them away. We have to begin to co-adapt with our global environment and move on a path toward a nearly 100% resource recycling. Now, so that may be sobering news, and it could be very sobering news if we return to the thought of us here at our New Year's Eve party, because as we count down the 150 years every second toward the future, we think, well, 50,000 years from now on this kind of time scale is not that far in the future. And if we're thinking about maybe a long-term agenda of the human race, if you're an optimist and you'd like to see some sort of sustainable development, I think it's just a matter of time before we migrate from the current growth-based economy until a new model, which is essentially recognizing that the only sustainability in the long run is flatlining and recycling. So with that, I am happy to entertain your questions, and I thank you for your participation.
How does the poll come out?
What's that?
How does your poll come out?
How does the poll come out?
The audience participation part.
Yes. So the first question is a good one. I have to escape and play from the start. So the question is, how did the poll come out? One moment. And another moment. And here we go. So we have low numbers here. But we have some people thinking about various optimistic solutions and some with man-made. I'm not going to ask you to revisit your vote, but perhaps I may have inspired many of you to think in 50,000-year timescale that of these two sustainable options, perhaps this one, confined to the inner solar system, is the one we should be thinking about. Yes, question?
Probably within 50,000 years, we'll figure out how to produce energy from controlled fusion.
So the question...
It's not going to make your idealistic, your optimistic prediction rather pessimistic.
So the question is, won't in 50,000 years we discover fusion? So I don't know the answer, but let's suppose yes. And you're talking about in terms of the ability to...
That produces a huge resource.
It produces an energy resource, yes, but it will not help us keep digging deeper and deeper and finding additional metals in the ground because the crust is enriched. Yes, right. So, right. Right. And of course, then we recycle our available. Yeah, sure. So that, I think, falls, whether we convert to solar or nuclear of any kind, certainly fusion, I think that could land us still within the confines of this. But it's a transition that I think we have to make on the timescales that we're thinking about of tens of thousands of years in the future.
I mean, it'd be interesting to compute how much energy we have to be able to produce through whatever new methods in order to sustain, say, a 0.5% per annum growth rate or 0.1%, whatever, some positive rate.
Right.
And it might not be so crazy.
Yeah, I think the problem with any kind of annually compounding function is it blows up. It always has that curvature and it always goes steep at some point. So the transition, no matter what we do, we have a finite amount of resources.
If we take the limit of the production of energy to be given by E equal mc squared, then presumably, we can go for quite a long time with a fairly small growth rate, assuming that we have some degree of efficiency in converting mass into energy.
I guess my point is that, well, first of all, I mean, I'm sure there are experts in the room about fusion more than I, but this fusion is one of these fields that it always seems like the answer is just several decades away. But you know, we're talking about long time scales. That may be it.
We're only a second or two away from
Right. Right. Yeah.
we haven't gone very far.
Yes. Okay. Thanks. Yes. Go ahead.
I want to try to articulate a very naive question. We've been around for 4 billion years Earth-wise. Why hasn't friction or something stopped all this plate movement? Where's all the energy?
Okay, so the question is, a good question. The question is, where does the energy come to drive the plates? And that is, there is frictional energy, but it's not a major impediment. The fact is that during the accretion of the Earth and the moon-forming impact and the segregation of the Earth's dense core from a homogeneous starting position, and the short-lived radionuclides such as aluminum-26 that were available in the early solar system, these are all sources of energy which are, in a sense, trapped inside the Earth and having to get out to space. And the energy is sufficient to have generated convection in the mantle, boiling pot kind of tectonics, but at very, very slow scales, convection in the mantle sustained for at least 3 billion years. So that's the energy is coming from two parts. One is the original heat from accretionary processes of the planet, and the other part is from radioactivity, which is greater in the past, but is still quite a large player with potassium, thorium, and uranium inside the Earth. Thank you. And we'll continue, sure. Yep, we have every reason to suspect that plate tectonics should be going on in the future for hundreds of millions, maybe billions of years. Yes, question on this side.
Would the 3 sevens indicate that our actions will determine the future?
The 3 sevens. Yes. Yeah, right. The 3 votes of 7. Sure, right. Right. No fate but what we make. Exactly. Well done. Yes.
Well, I was confused about the poles as defined by the axis of rotation
Yes.
and defined by the magnetic poles.
Yes.
My understanding is they drift.
Yes.
So that changes the way you do your
Right.
calculations.
Yes. So the question is, how good is the assumption of the coincidence of the magnetic pole from the rotational pole? And that's a fascinating and rich field. It requires lots of data, big community of people working on that. My explanation of that was very rapid, and I'll repeat the important element here. Even though there's lots of wobble and drift and occasional reversals, what we have determined, we as the community, essentially since the 1940s, we started making measurements of rocks, that on average, if you can average over a few thousand years of time, that all those little wobbles will average right out on top of the rotation axis. Yep. Whether it's north one or south one in the reverse polarity. And these were studies that were done in the 1940s and 50s, first on lavas from Iceland, and then that kind of result has been repeated from volcanic rocks and sedimentary rocks all over the world. Thanks. Yes?
So these plates moving around, they seem to move in one direction for a long time and then maybe stop and move back again through the energy that you just mentioned.
Yeah.
So why is that? Do you have any models of why these things move around, when they stop and reverse, et cetera?
So the question is, why would plates move to a certain point and then shift gears or shift direction and move to another position? And do I have any insights into why that may be? That's a tricky question. We have a really good handle on where the plates have been for the last 150 million years because we have those intact ocean basins that document step by step the motions in between the continents and the motions of the plates. When we go back to more ancient times, when I make movies, because I'm human, I'm making subjective decisions on what to do with the gaps in the data that we have. And so there are many constraints, but there are also many degrees of freedom. And I make my movies such that they largely conform to the patterns and the speeds at which the motions have happened over the time that we know very well. So you could say that my movies from the ancient past are confirming the modern styles and speeds, but that's a circular argument. There could very well be times in Earth's history which have surprises for us, where things move in different. So I'm really not at a point where I would say for certainty what are all the dynamic forces that are acting on the plates to move them around. But what we do know from the last 150 million years is that plates can turn around and then shift directions, and that the main plate driving force is thought to be the weight, or we say negative buoyancy, but it's the weight of these big subducting slabs of ocean lithosphere that are diving back down into the mantle. And the Pacific plate is a good example where 45 million years ago it had been moving north and then suddenly shifted to go northwest. And that's thought to be due to different slab pull on different sides. It's almost like if you were, you had a mezzanine level with a carpet and you could reach up and you could pull the rug in one direction and then you could pull it in another direction off the edge of that mezzanine balcony. These slabs, sometimes they detach and break off. Sometimes subduction zones turn into other kinds of plate boundaries. So
It's difficult to predict what's going to happen in the future then, I guess, right?
absolutely, and that's why I'm throwing so many disclaimers into my future models, which are just animations. Yes?
So you said that Australia's moved as far east as it's going to move, and North America's moved as far west as it's going to move. That sounds as if the Pacific plate is some kind of rock that's sitting there and keeping everything else in place.
Yeah. Good. So the question is, if I've said that Australia has moved as far east as it's going to go, the Americas have moved as far west as they're going to go, that the Pacific, there's something in the Pacific which is impeding the further westward motion of the Americas and the further eastward motion of Australia. And that is, in fact, the essence of our model, that the Pacific is a site of big, broad mantle upwelling, and that's been known for a while. And so this big, large zone of rising rock in the mantle that comes up to the East Pacific Rise at Easter Island in the Galapagos, spreads out in both directions, and then sinks underneath Japan or underneath the Andes. That big upwelling structure in the mantle is what is impeding the further motion of plates to go over the top, because it's a zone of divergence. Thank you.
Maybe I'll take the last question here.
Okay.
Now, one of the big events in your story was the breakup of Pangaea. But it was impressive to me that before Pangaea, you had a bunch of very small pieces. And so the net result of all these movements was to go from many small pieces to big ones, even though Pangaea broke up. So what's the underlying explanation for why we start out with little islands that have ended up with big continents?
Right. So is continental size increasing with each successive cycle? What I didn't show I showed a little bit from the ancient 2 supercontinents before Pangaea, but we suspect that the ancient supercontinents may have been just as big as Pangaea, and there may have been continents just as big as today's continents, except the individual fragments that you see colliding to make Pangaea themselves were spawned from earlier, larger amalgams. So there's this kind of shuffling that goes on. And if you think about a deck of cards and the height of the cards in the stack of your deck, and you may have several substacks, and these could be your continents. And the motion of continents is the transfer from one card from one pile to the next, or a group of 3 cards from another pile to the next, and everything's shuffling around, which is what makes it so difficult, actually. But your question is exactly the kind of question that I hope that our research can address in the future, about the sizes of continents and that kind of question.
Terrific. So on behalf of everybody here in the room and anybody watching out there in cyberspace, thank you very much for such an interesting and thought-provoking talk. Audience, now, let me invite you to 2 things. One is we have a reception in the common room right now, and let me invite you to come back and hear Susan Hyde about democracy on the 25th of April. Thank you.